Okay. We're filming? Okay, great. So we just defined, did I call it the fixed part? We just defined the inertia action. This is called the fixed part of the tape module because it's the part that is fixed by inertia. This is easy to remember. There is another smaller thing which lives inside it, which is the toric part. So T. So when we talked about semi-abelian varieties, we said there's a torus, zero torus, semi-abelian thing, abelian thing, zero. But that's, so like semi-abelian things have this sort of torus living inside, and because the quotient is abelian, you can kind of see that you couldn't make the torus any bigger if you wanted to. This works very generally, and so if I have my, say, how generally? So very generally, certainly generally enough for this, if I have a group scheme, then it has a largest subtorus. But I forget what I have a group scheme over, say, algebraically closed field. It has a large, or even over a field, it has a largest subtorus. But I forget what the assumptions are. The assumptions are certainly set. So in this case, it's smooth commutative and everything is certainly fine. I'm pretty sure things are more general, but let's not worry about that. So in general, we have T contained in the N0F, the largest subtorus. So remember, a torus is a thing which is a form of GM.
No, but your F is separately closed. So
it's even just.
So it's just GM to some power.
Yep. Yep. So the thing which like takes some one has to prove is that there is a largest subtorus living inside here. Well, this is true. I mean, one could say an awful lot more about the structure of the quotient type, but we're not going to try to do that. So we have this largest subtorus, and then we can just define the toric part of the tape module, sort of in the maybe obvious way. So T of a toric. So this is just say X in T a. So if we have something with the inertia invariant part, well, that's just the N0 part. So if we have an X in here, it certainly lands in the tape module of, it lands in here. And then we can ask if it actually lands in the torus, such that X lands in T. When we reduce modulo the, when we base change to little f. Okay, so that is what it is. And so we end up having T L A toric part, which is contained in T L AI, which is T L N0, and this is contained in T A. And so here it's maybe good to think a little bit about the ranks of this thing. So the rank of this thing as a ZL module is just 2 times the dimension of A, and the rank of this thing as a ZL module is just the toric rank, so it's just this R here. You don't get a 2 coming in anymore, because if you look at the roots of unity in a torus, then the rank is, there's a mu n has n elements and not
N squared.
Excellent. Okay. So
maybe you already said this is T unique.
Yes.
Okay, that's good.
Yeah, because if you have 2 of them, you just take the subgroup generated by both, right?
Okay.
So
but then you have to check
do that, and that still works. It's still a torus.
And yeah, and this is the step.
This works in the commutative case.
Okay.
Then they are conjugated.
Oh yes, and generally conjugating, but of course conjugating in a commutative group is uninteresting. So awesome. Okay, so here we have we're breaking the tape module up into pieces, and we can start to see how we might get a handle on like what the toric part, because we want to show that the toric part is sort of quite big, but we want to show there isn't any additive part. So I haven't defined an additive part. Okay, and so what we're going to do now is we're going to look at the Weil pairing on this thing, and we're going to look at certain parts in this decomposition will be orthogonal to certain other parts, and that's really the key technical ingredient to the proof. So we want the Weil pairing. So I could just say, well, you want to know what the Weil pairing is and carry on, but I found this really nice way to describe it. So shall I do the Weil pairing? Cool. Okay. So this is using this bi-extension machinery. So I'm not going to define bi-extensions in detail in full because it will be very painful. but I'm going to use a little bit about, I'm going to show how sort of a small part of the definition of by extension gives you the Bay pairing in a sort of beautiful and natural way. So, okay, so the Bay pairing actually goes is a pairing not on this thing, but it's a pairing on TLA cross TLA dual. One can choose a polarization, which we'll do in a little while, but let's not do that just yet. Let's sort of do it properly on A dual, because things are much cleaner. So here we have to be careful what the pick 0 means. If you think of it as degree 0, you will get confused because there is no reasonable notion of degree, but if you think of it as the connected component of identity, then you'll get the right answer. Because you want this to be, obviously, an abelian. This thing will generally have many connected components, but you want to pick the one containing the trivial bundle, and it's the dual abelian variety, dual abelian scheme, whatever. So there is the identity map from A dual to itself, and this gives us an element of pick 0 A over K of A dual. Neat stuff, right? So notice, this gives me a line bundle L on A cross A dual. Essentially, by definition, of pick A of T is basically line bundles on A cross T. Basically, it's a terrible thing to say. Plato gave us, lots of detail about how this works, and exactly when can you represent an element of this by an honest line bundle. But here, notice that because our things are abelian schemes, we can rigidify the line bundle. We can always rigidify the line bundle along the unit section. So, rigidified. Which is it? Should be the unit section of this thing.
For both. It doesn't matter, it's for both. Because the 0 of A dual corresponds to the trivial line bundle.
Yeah. How do I, yeah.
Well, along the union of the two.
Is this a reasonable thing to say? Yeah, I believe this.
Union, I think, right? And they intersected at the 0, 0. So that's nice.
Okay. Okay, I will think about this more, but it's not fun of you to watch me think about things, so. Okay, so the thing is that once we have this rigidified line bundle, I guess because as a line bundle over here, it's rigidified along this.
So what you wanted was E.
What I wanted was E.
Yeah, because you look at the family of where
of
the A's are the fibers.
And then it's E.
Right.
Yeah. Cool. Okay. And so rigidified line bundles so it's not only a rigidified line bundle, it's actually a by extension, whatever these are. So what do we, so I'm not going to, as promised, I will not write the definition, but what do we get out from it being a by extension? It is a by extension in particular. So if you want to know what a by extension is, look in this SGA study part 1. But what is sort of the concrete things are, suppose we have if, say, a point A, comma, A cross, is in A cross A dual of S, some scheme S, we get, so we can restrict our line bundle to this point, we get which is something we can call L A prime on S. So a line bundle, if S is a point, it's a line bundle. And we have canonical isomorphisms. This is an A1 and A2. Okay, so these are both line bundles on S, and if S is, for example, a point, then the fact that these are isomorphic is a totally vacuous statement. The key thing is that we have a distinguished and chosen isomorphism here. This is going to be really important for what comes later, because the Bay pairing will be an element of GM, which will come from an automorphism of a line bundle. And if you just say, well, they're isomorphic, then you won't know what the automorphism was, and you'll be doomed. And there's a sort of corresponding thing where I swap the okay. So we have these two things, and we have, even better, such that the two ways of making. So what if I put like a1 plus a2 comma a1 prime plus a2 prime? I can apply this and then I can apply this to each of the factors. Or I could apply this and then I can apply this to each of the two factors. So it gives me, so these two, doing these things in different orders gives me two ways, gives me two isomorphisms in the following things. Guess what comes next? If I haven't made a typo. Okay. So we get there's two ways to build this, either do this, then this, or do this, then this. And they are the same. So the two isomorphisms are actually the same thing. Okay, so in particular.
Sorry, can I ask?
Yeah.
Is there also some kind of compatibility concerning associativity of additional non-factors? So if you have like a1 plus a2 plus a3, there's also two ways to go.
Almost, not only am I not going to tell you the definition, I also don't remember the definition. So I think so, yes, but this is all I'm going to use.
Okay.
I'm not claiming this is enough to tell you what the by extension is, only that these are things followed from, like.
Okay.
So L of 0 A prime is canonically isomorphic to L of 0 plus 0, sorry, is equal to L of 0 plus 0 A prime, which is canonically isomorphic to L of 0 A prime tensor L of 0 A prime. And then these are line models like a tensor with the dual, so this gives us a canonical isomorphism. It gives us a canonical, if I put this first factor to 0, I get a canonical trivialization of this thing. And
But that is
symmetrically.
just the rigidification, isn't it?
Yeah. That is the rigidification.
Oh, excellent. Okay.
Yeah.
I can also do it on the other factor. And so on the other factor, we also get which would have been a reification if we had chosen the other one.
Well, there is a unique one that extends it from the point 0, 0.
Yep. Okay.
So
Yes.
yeah.
And so, yeah, this. Okay. Wonderful. So this was all just like 3 boards worth of formal setup. So let us profit from this to define the Bay pairing. So the Bay pairing, remember you input torsion points and it spits out points in GM, or more precisely in mu. Well, if you have integral for roots of unity, so if you put in some n torsion points, you'll get out things in mu n. So now, let's say A is in so notice that we never used our base with a field, so this just works like for abelian schemes of any base scheme. It'll give us a map of the Bay pairing is a map of pro groups, unit group schemes. Oh, I'm confused. I guess pro.
Why take a limit or a co-limit? You can just work with these, right?
Yeah, that's fair.
Yeah.
I agree. Okay, so then. So let's look at the fiber LA, comma A prime. If we take the nth tensor power, then by following through, we have our canonical isomorphism here, we have our equality in another canonical isomorphism, which if you like is the rigidification.
You are using what I said.
Yeah.
Oh, you're right. Yes. Yeah. Okay, so we can do the same on the other factor, again using what I just said, this associativity of addition thing. So now we've got a map from OS to OS. And this is, so this is our, does it have a name?
you should put an n in the notation now, because A and A prime do not have to have order n or so. I mean, the n is extra information.
Thank you. Yeah. So, okay. So the A and the A prime and the fact that we're just considering them as n torsion instead of this like n2 torsion or something gives us an automorphism of OS, which is just the same thing as a section of GM of S. So that's all we also like it to live in mu n ideally. So we have this phi A comma A prime in GM of S. We want it to live in mu n. So
maybe the n as a superscript is a bit dangerous.
oh yeah.
Yeah.
Good point. Yeah. Given it's going to be,
You're going to take the power, so.
I'm going to regret that. Yeah. Okay. So I'd like it to actually be an nth root of unity. So this gives us a map from A n cross A dual n to Gm. Now for group schemes, we want it to land in mu n, but notice that L A comma A prime tensor n squared. That's just this thing. Again, we can sort of. So what can we say? So we have sort of essentially. So I'll be somewhat speedy, but essentially we sort of took two different ways of trivializing. But if we pass to the n squared thing, then by what we said down here, these two ways of trivializing must coincide. So, and the two ways of trivializing coincide by this thing. So, phi is identity.
But you could also have said that that map to GM was a pairing, right? It is bilinear.
Yes. Oh, and then
Yeah, then n times it is trivial because
true. Yeah. Okay. Well, that would be a bit quicker. Yeah. Okay. So one way or another we've got ourselves this thing, and of course, like we have to be a little bit careful. Like if we start to change, like I want to let L be, I want to place this n by some power of L, and then I want to fit these together as L varies. Of course, I should be careful that the viewing a thing which is a L squared torsion is a thing of L torsion, and the restricted map is the same. There's something to check here. So these assemble into a map from TL A cross T L A dual to TL of GM, which we also call ZL of 1. This is this free ZL modular rank 1 with the Galois modular structure coming from sort of roots in unity. So this is the famous phase pairing. In Silverman, it's defined by some shenanigans with divisors and evaluating functions. You can also define it using Hilbert symbols if you want. If you really like Hilbert symbols, I guess you'll like that more. But I don't know. This is very nice. This works for any base scheme, gives a map of root schemes. It's pretty cool. So, we have one more page of notes. So if it's okay, I'll go on for another 10 minutes or so. If you get very bored, you can sleep, and if you need to leave, you can, of course, leave. I'm going to choose a colorization.
So, David, one question about civil construction. There's also a way pairing where we just let n be any isogeny, right? But then we can't get that through here. We really rely on n being an integer here.
No, because I'm not going to try to I presume that you could still use this machine.
I mean, the kernel of the isogeny is in some n portion.
yeah, but you can use it. But you have to use the dual isogeny as well.
Yeah.
Actually, there is also a nice way to so what do? You view the dual as the x1 of A by GM.
Okay.
And now if you have any isogeny, say alpha, then you have a short exact sequence, kernel of alpha, A, or A prime, say, A to B. and then you apply, this is a short exact sequence, and you apply the Holm to GM to this, and you get a long exact sequence which tells you exactly what happens. Right?
But that will give me.
Well, it gives you, it identifies the kernel of phi with the Caché dual of the kernel of phi dual.
Okay.
So that is exactly what
Oh,
makes
and
a
then-
perfect pairing between these kernels.
Beautiful. Yes.
Yeah.
Nice. That was nicer than mine. Never mind.
Well, this is also very.
I think.
No, this, yeah, I mean, this puts it in one thing. But so you A dual is the pick 0 of A, but it's even better to say it's the x1 of A by GM. Right? But this does it. You use this. Yeah.
Awesome. Okay. On to the orthogonality theorem. So I'm going to choose a polarization which is going to give me an isomorphism. And so then I can apply my.
So you have a polarization of degree prime to L?
Right, I hope so, but I couldn't actually.
Because, well, maybe tensor with Q, this is an isomorphism, it probably doesn't matter, right?
Yeah, so I'm just
So
confused.
you don't care. I mean, it's a thing with which these are ZL modules, so it's injective map
Yeah. So it doesn't actually matter. But
with a finite co-kernel. I think I would be surprised if you need that it is a
I think you're right.
isomorphism.
I think you're right. On the other hand, it will simplify things slightly, so
Okay.
let me choose my switching degree. So then we have this wonderful orthogonality theorem. This theorem 2.4 from SGA 7.1 and 0.9. So I just want to, I'm going to make some notation. So U is the sigma of A, V is the fixed part, so I'm stating but without, so this pairing we've defined as a perfect pairing. I'm not, I mean, it is a thing that is true. So we can take this, we can take the orthogonal to V under this map, well we can take the orthogonal anyway, but now the orthogonal will be V again, so it's somehow healthier. And we can define W to be V intersect the orthogonal, so this is order notation. Content of the theorem, the first part is that W is equal to T L A T. Remember, this is the toric part of the tape model. So this is really something which is, I mean, this really takes some, one has to make some argument here. It's not especially long, and it is quite nice. But I mean, here you're using sort of a geometry of what the fibers of these models look like. It's kind of fun. Okay, and so I'm going to sort of roll into the orthogonality theorem some nice diagram. In SGA, this comes a little bit after the orthogonality theorem, but I'll let me cheat and pretend to be part of it. For some reason, this diagram isn't from right to left. It could be left to right. Okay, doing that. So we have some inclusions of submodules. 0 is contained in V. In W, W is contained, well, at the intersection of two things, it's certainly contained both of these. They're both contained in the sum. The sum is the orthogonal of the intersection, perfect pairing, thing. This is contained in U. Okay, so the fact that we have a diagram is nothing special. What are the indexes of these arrows? So I'm going to label each arrow by its index, sort of as of Z, L module. And this is mu. What is mu? So mu, toric rank of A, the dimension of this T. So we had a T which was the largest torus, and that's the dimension of this T thing. So also this thing has rank mu by this pairing game. What else? We also have the abelian rank of the.
No, it's additive, I think, right? Or abelian? Okay, go ahead.
Lambda is the additive rank. What is this? This is okay. So we have the torus. So the torus. We have this torus, which is the largest torus inside N0F. Well, then have the abelian thing. Is this the largest abelian? So there's sort of also a largest abelian quotient, and that has a dimension, and that's called the abelian rank. So a dimension largest abelian quotient of N0F. And then we have this thing called the additive rank. So I'm going to be very cheap and just define this to be the leftover rank in some sense. You can also, like, more properly, you should. There's a nice decomposition of this group scheme as an extension of some additive thing, and this is actually the dimension of the additive part. But let me very cheaply just define it to be this difference. And so if we want to prove our thing is semi-abelian, we want to prove that the toric and the abelian part sort of fill up the whole abelian variety. So semi-abelian, if and only if lambda equal to 0. Okay, why do we define this alpha and lambda? Because they fit in this nice diagram.
There's no two.
I think you should
Should I
move
not?
some indices because
I think I should not have these two. Oh, also what? Yes. This should be a lambda.
yeah.
Lambda should be an alpha. Okay.
No.
No. This is.
So the abelian part contributes to V, right?
Yes.
So that is the alpha. It goes there to
This
alpha.
this
That's
actually
right.
makes sense.
Yeah.
Yes, we've
Yeah.
seen this, and so we also get this.
Yes.
Indeed. And this is sort of the
That's what
what
remains.
remains.
Yeah.
Why do I want to?
I think it is 2 lambda
I think
because
it's 200.
the alpha plus lambda plus mu is the dimension of your abelian, of the fibers
Yes.
of the abelian variety over the fraction field. And so the rank of the module is twice that, right? So if you sum everything up, you should get 2 alpha plus 2 lambda plus 2 mu.
Awesome. Yes. So if I
And,
choose
and,
either of
and
these
the only
paths,
one term was
sum-
missing, so you can solve the equation.
Yes. So either of these paths, the sum must be 2 mu plus 2 plus 2 lambda, and so I can, whichever one I forget, I can fill in. It's very convenient. Okay, so now we can prove the semistable reduction theorem in the last couple of minutes, if we remember the eraser. I'm going to make another tiny pattern of video. I'm sorry.
Maybe.
And a new battery. Oh no, this is a terrible.